Assalamu alaikum student and colleague. Welcome back on my channel. Today we have a continuation of our previous lecture series that was related to the concept of the vector space. And now I will conclude that topic of the vector space. I think after completion of my this video, you will be able to understand the use of vector space, particularly in the field of advanced microeconomics. Remember, the topic of this that topic I selected because it is most frequently used, particularly in advanced studies of the microeconomics, as well as you may apply this kind of the concept in the econometrics and the macroeconomics areas. But today we will focus towards specifically related to the advanced microeconomic theory. Okay, and now the concept or the topic of discussions today we have linear combinations, convex combination, linear span of vector, and similarly subspace of vectors, linearly independent and dependent vector. And now I will try to explain you okay, why these concept we apply particularly in advanced microeconomic theory, and why we are discussing these topic here. That is very important because most of the teachers explain you okay, now how you can find out the linear combinations and but they do not tell you okay, why you have to find out the linear combination of the vectors and what is the need of here or particularly in your area of the microeconomics theory. Clear? So now today in the previous lecture we differentiate between the linear combination and the convex combination of the vectors, and then we started okay, how you can define the linear and convex combination of the vectors. Okay, first of all, just recall the concept of the linear combination and the convex combinations, and I just want to explain the difference between okay, how you can distinguish these two concepts, particularly in the area of microeconomic theory. So today let's consider, for example, for example, for example. Now, for example, okay, and let's say we have a vector A, and this is vector B, right? And you can define a linear combination of these two vectors in this way. For example, this is vector C. That is the linear combination. What? For example, alpha 1 A plus alpha 2 B. This is kind of the linear combinations. Okay, and we have discussed that okay, now uh, that linear combinations is defined over the field of real number. Okay, because the topic of discussions is particularly the real number series. We are not going to discuss the complex number because the complex number I told you that is it is not the part of our discussion here. Okay, so first of all I can explain this one. Let's see how you can explain this is kind of the linear combinations. Up now, in that linear combination, you can define in this way as well. How you can define, for example, this is your vector A, and now this is another linear combination, let's say alpha A. Okay, so this is kind of the linear combination, right? So these are two ways to define the linear combination. One important thing is here, there is no restrictions. What? The value of alpha may be greater than equal to 0. Okay, that value may be greater than equal to 0, or this value may be 1, 2, 3, 4, 5, whatever. The value of alpha may be, for example, 0, 1, 2, 3, and so on. What I am saying, there is no restrictions related to the weight of or the value of alpha here. We can define the value of alpha in any way, either it is 0, 1, 2, 3, and so on, or it may be, for example, less than, let's say, less than 1 and whatever 0.5 and so on. But what the important is here? For example, if this value is less than 1, let's say it is, for example, 0.5. So how you can define this linear combination? This is, for example, A. Okay, now this value is alpha A. You got my point? Because it is 0.5, when we divide this value of vector with 2, so you will have the less amount of vector as compared to previous one. Clear? So that is when the case is alpha value is 0.5, so your linear combination will be this one. Now, what is the utilization or why we discuss this concept of linear combination here? I will explain later. First of all, just I want to explain or create a difference between the convex combination. Okay, how you can define the convex combination. For example, convex combination. Okay. Yeah. So in case of the convex combination, what? For example, this is another vector A. This is vector A. This is vector B, and this one is vector. See. So these are three ways. Yeah. This one. Okay. And this one. Okay. Now this one. So now what about this? Is, for example, let's say the convex combination of A and B. Convex combination of A and B. Similarly, this is another convex combination. Convex combination. And so on. This is another convex combination. What we have concluded here, look at this diagram here. Now we are extending the value of vector by taking the linear combination. How we are going to take the linear combination? For example, we are multiplying these two values, let's say by alpha something, or take a linear combination. But in this example, what we need to discuss, we discuss here we discuss how you can define the linear combinations in this way. So here the value of alpha is greater than 1 because you are going to extend the value of vector A. But now you are going to take the average between these two values. So in this condition, the value of alpha never be greater than 1. It always lies between 0 and 1. That is the restriction here. So the value of alpha here, alpha always lies between 0 and 1. Okay. Another restriction is here. the alpha always be greater than 0 in case of the convex combination. Alpha always greater than 0 and it lies between 0 and 1 in case of the convex combination. Now, so how you can define the convex combination of A and B? Something like this one: 0.5 A plus 0.5 B, or so on, 0.3 A plus 0.7 C. Another condition is that the sum of alpha should be equal to 1. So in case of the convex combination, these are the restrictions, that the value of alpha should lies between 0 and 1, and it is greater than 0, as well as the sum of alpha value is equal to 1. Now what the important point is here, okay, why we are discussing this concept in case of the advanced microeconomic theory. Okay, when we talk about the production set, or we talk about the production sets or the consumption sets. Okay, in case of the consumption sets, we have a set of budget, okay, right, or the indifference curve. In case of, now, in case of production set, in microeconomics, yeah, what kind of the properties you will have? You have a certain important properties. What are the important properties here? Okay, we say that the production set that is capital Y, and we say that it is belongs to Y. Y is production plan. Okay, we discuss in advanced microeconomics that the production sets is belongs to production plan. Production plan may be feasible or infeasible, but the feasible part of the production plan is called production sets. Okay, the feasible parts of the production set is called, production plan is called production sets. Now why I am discussing this concept here? What are the certain properties of the production set? First of all, in case of the production sets, we discuss that. What? Just a minute. So in case of the production set, we discuss non-increasing returns to scale. We discuss non-decreasing returns to scale. These are some or constant returns to scale. These are some important properties that we discuss in case of the production theory or the theory of the production. And we can say that these are the three important properties of the production set. Now I am going to relate these concepts with our topic of the vector space. what we assume that the production set is a vector, okay, and defined over the field of real number, because we discuss in advanced microeconomics ke every production set is a part of vector. It defines over the field of real number. Okay, what are the important properties of the production sets? Okay, first of all, we say that non-increasing returns to scale. What does it means? Okay, by non-increasing returns to scale, let's say we defined, okay, this is a production set, for example. Commodity space, okay, commodity space. In that commodity space, that you defined any value which represent a vector which has certain important properties. What are the properties here? Okay, by, for example, if it is y, any vector of output vector, clear? It is any vectors. So what does it means? It means that it has non-increasing returns to scale. What does it means? That non-increasing returns to scale, it may be a constant returns to scale or decreasing returns to scale, but it never increase. So in that condition, we may apply the value of alpha y in case of the production theory, right? So the value of alpha means that it is less than equal to 1, right? Either it is equal to 1, non-increasing returns to scale. So the value of alpha may be less than or equal to 1, right? So then you can, that value may be scale up or scale down in case of production theory, right? So it means you can define or you can relate this linear combination with this production theory, right? The concept of the linear combination with this production theory. You have to be clear, guys, bacha, you have to be clear about the concept of the production theory, otherwise you won't be able to understand how I am going to relate this concept with the production theory. You have to know about all the properties of the production set, okay? So first of all, read out these properties, then you can able to understand what is the use of this factor concept or the linearly independent concept in that topic, okay? And now, second important. So what does it mean? Non-decreasing. So it means that it is equal to 1 or less than 1. So it means that now that one, it is in this way. Clear? Non-increasing returns to scale. So value of alpha will be alpha y like this one. Either it is equal to this one. When it is equal to 1, so again that will be equal to alpha y, or either it is less than this one. Okay, so you can define in this way. Similarly, ab now first of all I am not going to discuss that how you define a production set, because it is another technical debates the production set will be like this one. So we are not going to discuss like this one. So just I am going to relate how you can define the increasing or decreasing returns to scale. Okay, so that is the important thing, right? So first of all, ab now for example, similarly non-decreasing returns to scale. So in case of the non-decreasing returns to scale, you can like this one, where value of alpha greater than equal to 1. Okay, so it means in case of the production theory, when you relate these properties with the production set, or production sets itself a vector. So now there is the use of linear combinations of production sets in case of these three properties: non-increasing returns to scale, non-decreasing returns to scale, constant returns to scale. Clear? Now, how you will apply the concept of the budget set in case of the convex combination? Okay. Now, in case of the budget set, convex combination and budget set. Okay. We defined, for example, the budget set in this way. Okay. This is kind of the budget set. Budget sets that is, for example, B, right? That is B, which is equals to what? Ultimately, for example, it is X and this is Y. So now the budget set is can be defined the, for example, the area which represent by this one. This is all the possible combination of X and Y. And now we take the prices here. So now what is the values here? For example, this is Xi or X1 or this is X2. Let's say. So how you can define I equals to 1 to 2, and this is P1, Pi and Xi. This is your budget set. And I am saying that budget set should satisfy the condition of convex set. And it is kind of the convex sets. What does it mean? It is the kind of the convex sets because all the possible combination of price and commodity expenditures lies in this area. Clear? Or this is the kind of the convex combination, for example, which is lie on that line, or all the possible convex combinations which is lie in this area, they are convex sets. Okay, so now you can say that in case of the budget set, the convex set, the property of the vector space is applied here. So that's why we discussed the concept of the convex set in particularly in case of the vector space or the theory of the vector space. Clear? So now I just going to explain how you are relating these technical concept with this theory. And similarly, when we define the consumption sets itself a property. What is the property of the consumption set? What one important property of the consumption sets when it is feasible sets? So in case of the feasible sets, one property is convexity of the sets. So it is another important property in case of the feasible choice sets. Okay, that we discussed in the consumer theory as well. Okay, now move forward. How? Yeah. Okay. Okay. Now the one important. So we have covered this convex sets and the linear combinations. Okay. So the linear combination as well as we defined in this way. For example, this is, let's say, the another possible way of the linear combination. Just discuss here. What, for example, take another example of the linear combination. Okay, for example, set of linear combination, or we can say that the another kind of right? What? Yeah. And yeah, x, for example, this is 0 0 0, right? And another vector of the choice is what, x2, that is equals to 0 3 3, and which is the x2 that is equals to 0 3 3. And similarly, there is another kind of the vectors is x1 x1. Okay. What about this one? 1 and 4. X1 is 1 and 4. Just a minute. X1 is 1 and 4. Yeah. X1 is 1 and 4. Yeah. 1 and 4. 1, 4, 2. 4, 2. Okay. So this is kind of the linear combinations. Is, for example, what the B is what? Alpha x1 plus alpha 2 x2 x2. Clear? So you can define, that is the linear combinations. How you can define that? Okay, ultimately you can find out the value of alpha and beta by the linear equation, but we are discussing that the B is, for example, let x is a three dimensional dimensional vector space, and that is what, x equal to what, 1 4 1 4 2, and similarly 0 3 0 3 3, and 2 4 2 11 7 2 11 7, right? So this is the value of x. Now you can define that. I can write this in this way. It belongs to 3 by 3. Okay, three-dimensional space or the vector that you can define in this way. Okay, when we take the linear combination of these two vectors or we sum, so if the answer lies in this way, okay, if we take the linear combination of these two vectors and that linear combinations belongs to this one, so we can say that x1 and x2 is a linear combination of vector x. Clear? That is it is my point here, right? How you can say that? We can say that take a linear combination. How? For example, 2 1 and 1 3. Take any two vectors. For example, 2 and 3. What b equal to? For example, b equal to 2x1 is what? 1 4 and 2 plus 1, okay, and 0, 3, 3. Okay, the value of alpha greater than equal to 1. Right here, that is the condition is here. Alpha I. Because we talk about the what, not the convex combination. I talk about the linear combination. That's why I'm saying okay, now the value of alpha is greater than equal to 1. Just take the example, solve this one. So 2, 8, 4 plus 0, 3, 3. Okay, so what about this one? 2, 11, 7. Okay, so it is the column vector. This column vectors is belongs to this one 2, 11, 7. So it is one possible linear combination. One possible linear combination. So that belongs to X. It is one possible linear combination. Okay, it is the one possible linear combinations. Now there is another technical concept is the linear what? The linear span of vector. What about the linear span of vector? Linear span of vectors. What does it means the linear span of vectors? Linear span of vectors we can write in this way, that is for example ls, the linear span of vector ls. What does it means? What? Summation I goes to 1 to n alpha I xi. Clear? And alpha I again belongs to field of real number f and xi belongs to vector space. Okay, vector space. So this is the linear span. What does it mean? Ki all possible linear combination, set of all possible linear combination, set of all possible linear combination is linear span of vector. Linear span of vector. All possible linear combination is linear span of vector. So now you can take the all possible linear combinations. For example, if we have another kind of the concept or another combinations and we get the value of, for example, we take another value of alpha and multiply and then add these two column vectors and get the value which lie, for example, it may be 1, 4, 2 or 0, 3, 3. So it means that these are all possible linear combination. If these possible linear combinations, if they lie in this vector or this commodity vector x, so we can say that it is called linear span of commodity vector. Okay, what it is called? The linear span of commodity vector x. Now, so one technical point is here. So it means that linear combination will be a single vector. Okay, the linear combination will be a single vector. One point is here. Linear combination, linear combination will be a single vector. Similarly, convex combination will be a single vector, but there are the condition what alpha greater than 0, right? Alpha less than 1. Why? In case of the convex combinations, the value of alpha never be less than 0. It means कि it never be negative. Clear? वो कभी भी negative नहीं हो सकती. There are the conditions. Okay. And the sum of alpha I equal to 1. These are three important conditions. Okay. And but the linear span of vector is a set of vectors. Okay, the linear span of vector is a set of vectors. वो vector का set होगा. Clear? It will not be a single value. Right? Now the move forward. So now I have concluded here कि what is the difference between the linear combination, convex combination and the linear span. Okay, there are the technical difference between these three important terms of the vector space. In the vector space, another concept of the topic is subspace of the vector. Okay, subspace of the vector. Okay. What is the subspace of vectors? Subspace of vector. Okay. Subspace of vector V is S. It is also a vector that is S is a subset of V, clear, which satisfy these important properties. Important properties. What are the important properties here? Satisfy important properties. What are the important properties here? There are certain important properties. Number one is additive identity. Number two, closure property. Number 3, inverse of vector. Number 4, all laws. What are the laws? Associative and commutative laws. Clear? So all laws means ke associative and commutative laws. These should be satisfied. So we can say that it is a subspace. So how you can define that? Ki for example, it is V is this is V and this is S. Okay. So S is itself a vector space which satisfy all the properties and which is the subset of vector space V. Okay. Now one technical difference. The vector subspace always include a value of origin or 0. One important thing. S always include a value of origin. What are the values of origin? Just okay. So now, so there are certain important properties as well as it should have value of 0 vector. Okay. Why? Otherwise you cannot prove the additive identity. If it does not have the value of 0 vector, you cannot prove the additive identity. So it means that it always pass through the origin. Remember, it always pass through the origin. वो हमेशा origin से pass होगा. So it means, what does it mean? अब now again there is a question कि why we are talking about this concept. Second important thing कि if we multiply LS, so itself it belongs to V. अगर इसको किसी स्केलर कॉम्बिनेशन लेते हैं और स्केलर वैल्यू से when we multiply, तो that value should belongs to this one. So it means कि it should satisfy the convexity, condition of convexity. So it means कि whenever we talk about the consumption set, okay, so what does it mean? Consumption sets is a part of subspace. Clear? The consumption set is a part of subspace. One technical, another technical. It means that I can conclude that consumption set and production set are also subspace of vector. Why? Because in case of linear indifference curve, what does it mean? The consumption sets or the indifference set has a zero value of the commodity. Okay, if it does not have the 0, so it means that it never be equal touches to the x-axis or the y-axis. Clear? Second important thing, Okay, either the value of x is 0, commodity x is 0, or the commodity y is 0. Or second important thing is that okay, consumption set is when we draw indifference curve. When we draw a indifference curve, all the possible values from 0 to onward, these all are the part of consumption set. So it is kind of the subspace of vector. Second important thing, in case of the production theory, 0 is the part of the production set. Why we assume that? The shutdown is possible in any condition. Okay, firm can be shut down if it requires. So that's why the 0 is possible, or it is belongs to the part of production set. So to some extent we can say that the production set itself is called the subspace of vector. Now the last topic is linearly independent and dependent vectors. And why we discuss the linearly independent and dependent vectors in vector space, and how you can relate this concept with advanced microeconomic theory. Clear? Move forward. Okay, what is the linearly independent vectors? Linearly independent vectors, for example, S, x1, x2, and so on, xn, that belongs to vector space which defined over the field of real number. Clear? If alpha 1 x1 plus alpha 2 x2 and so on, alpha n xn equal to 0. What does it means? Implies that alpha 1 equal to alpha 2 equal to alpha 3 and so on, alpha n, it is equal to 0. The vectors x1 and x2 or xn are linearly independent vectors if, but if any value of alpha I, any value of alpha does not equal to 0, the vector is linearly dependent. Vector is linearly dependent. Acha. Now why we are assuming the vector is linearly dependent or the independent? First of all, I told you that in case of this one, alpha y and so on, this one, this is y vector and this is, for example, alpha y alpha value is greater than equal to 1. It is kind of the production set or whatever. So now you can say that it is linearly dependent. So in case of the linearly dependent, you will never find a unique value of vector. Never find unique value of vector in case of the linearly independent. Okay, sorry, dependent. When we apply the concept of the linear dependent, because when you have a substitution effect in case of the commodities, when there is a substitution effect, when there is substitution effect between commodities, between commodity vectors, they are linearly dependent. Okay. Similarly, when there is the substitution effect between input vectors, so they are linearly dependent, or input vectors, or linearly dependent. Okay. It means that one input can be defined in term of another input. Okay. The one combination of commodity can be defined in term of another commodity, but in case of, so linearly dependent. Okay. Now in case of linearly independent, when you will have a complement, so there is no substitution effect between these two commodities. So in that condition, the choice vector or the choice variable will be linearly independent. You got my point? So it means that depends on your conditions. When you will assume the two choice vectors or the two vectors are linearly independent or dependent, depends on your theoretical understanding and the theoretical concept. It is not necessary that always you will assume the case of linearly independent or the case of linearly dependent. Depends on your theoretical understanding or your theoretical foundations. So guys, that the topic was from my side. Just a minute, just I look at, is there any missing point here? Okay, no. So it means that now the topic of the vector space is enough with respect to the advanced microeconomic theory, and that was from my sides, and it is the conclusion of this 4 lecture series. And you can watch my initial videos or the starting videos of the vector space. I think I have 4 lecture series of vector space: lecture 1, lecture 2, lecture 3, and that was the lecture 4. Okay, so hopefully inshallah we will meet again with coming videos, and now I will going to start the topic of discussions again with the game theory and choice under uncertainty, that is related to the decision theory. So inshallah I have a complete course related to the topic of the game theory and the topic of the decision theory. So parallelly I will move both courses, so hopefully it will be beneficial for you. Thank you so much. Allah Hafiz. We will meet again, inshallah.